Hello, hello. uh, okay, and this is Bagalage Uma. So today I want us to look at the design process of a ribbed floor, specifically a hollow block floor or a maxispan. In our country we call it a maxispan slab. Yeah, but the principle is always the same. Okay. I think we have a guide that we are going to follow throughout this tutorial. The question that we are going to be answering, it goes that the ribbed floor is constructed with permanent fiberglass molds. It is continuous over several spans of 5 meters. So it is a continuous slab. So now here we have the material properties, the compressive strength and of the concrete, and the yield strength of the steel. So, and here it goes further and says that the section here that we are going to design satisfies requirements for 60-minute fire resistance. What this means, this specifically governs the width of our ribs. And it's from Eurocode what? Eurocode 2.1 part 2. The Eurocode that guides you through fire resistance. To briefly show you, I was able to extract a table from that Eurocode, table 6.4. You can check it out, and to show that our ribs do our slab satisfies the requirements of a 60-minute. And since it's a continuous slab, the minimum rib width is 120 mm. And then this is the axis distance from the surface of the rib from the bottom surface of the rib to the center of the ribber. It should be 25 to satisfy the fire resistance requirement. Remember that there are other requirements like durability, which in most cases governs the concrete cover. So to go back to our question, then the permanent load, the correct permanent load including self-weight and finishes is 4.5. Not that when you are doing your project you have to calculate for these values, and also get this value from your code, your country code. So our permanent load is 4.5 and our variable load or live load is 2.5. And here is our section of the slab, the longitudinal section of a slab. This is one span extracted from the slab. Let me try to make a simple illustration here. If this is the plan view of our panel, the extracted panel, this can have maybe this is the, let me pick a different color to draw the beams. Okay, these are our beams. Oh, sorry, I wanted to use a different color. Sorry about that. Okay. Yeah. Okay, let this be our beam. No, let me do this. Do it like this. Okay, so this is the plan view. This is the beam in red, the beam boundary. Then this is the center line of the beam. So our ribs, if the distance from here to here this is 5 meter. Oh, sorry. Okay. So now our ribs are running in this direction. These are our ribs. Okay. All right. Now then here the ribs are terminated at a distance of 600 from the center line of the support. So 600 mm. So this portion is made solid portion here. It's made solid. Both ends. These are our ribs. These are our ribs. And try to height them. Those are our ribs. And then this portion is filled with, sorry, I wanted to use a different color. Try that. With our hollow blocks. These are our hollow blocks. These are our hollow blocks. So in the question, the spacing from one rib to another, this spacing from here to here, the center line of the ribs, this spacing here, this, it's 100 mm. Okay, then the rib is rib is 125 mm. Okay. So now the first thing you have to do is to compute the load carried by a single rib. Remember now the load will be distributed from the top of the slab, from the topping, this topping which is 60 mm thick, to the rib. Speed the load transfer. For example, if we sing out this portion, so the load at this portion here distributed in a manner that half the load goes to this rib and half the load goes to the other rib, and same applies to the adjacent portion like this. It's also distributed in a manner that half the load goes to this rib and half the load goes to this rib, and in the end each rib will carry half its spacing this side and half its spacing the other side. So it will carry a load that occupies a width of the rib spacing, which brings us to the statement that each rib carries 500 mm the width of the topping. Okay. So therefore the ultimate load per rib will be given by the ultimate load per square meter times the rib width times the flange width. Yes, the flange width, which is 0.4 meter or 400 mm, giving us 3.93 kilonewtons per meter run of the rib. And then in the end, we get 3.93 by multiplied by the span, which gives us this 19.65. Okay, after computing the load, the next thing we do, we compute the design moment, all the design moments. And since we are dealing with a continuous ribbed slab, it means that the ribs are continuous over several supports. So, which means in each span we have support moments and mid-span moments as our critical moments. But we can't go on designing for each span, we have to design for a critical one. And from analysis, we find out that the end span carries the greatest moments, and then the first interior support, it carries the greatest hogging moment. The mid-end span carries the greatest sagging moment, so we shall design for that, for the bottom steel. And then for the top steel, we shall base on the hogging moment at the first interior support. Okay. For continuous beams, we have an option of designing the end support, of considering the end support fixed due to the monolithic casting of the slab. But if we are to follow this statement that the end span is always the most critical, so we shall design for that. Also, the end support restraint provided to the slab by the beam is not strong enough to treat it as a fixed support, just like that, provided by the columns to the beams, which means the beams don't give that fixed, they don't fix the slab in position the way the columns do. So we can as well decide to what this does, what fixed does is that some part of the moment, that the portion of the moment carried in the mid span is transferred to the supports. But now if we assume that the supports are pinned, that there is no fixed at all, and then we get the worst case. We get the worst case at the span, at mid span. So from the bending moment coefficients for one way spanning slabs, at the end span, which is our critical span, the coefficient is 0.086, and if we multiply that by our ultimate load, design load, which is 19.65 times the moment, the span, we get this as our design moment, our design sagging moment. This is our design sagging moment that we shall apply to the rest of the span. Once we design for this, then it means the ribs can't fail elsewhere, as the reinforcement that we shall have provided will be enough. Okay, so after that, after determining the moment, we now have to compute the reinforcements to resist this moment. From the formula that we all know, this formula is derived from the analysis of a section. This is a formula. Area of the steel required will be our design moment divided by 0.87 FYK. This is like this is also the same as FYK over material. The factor of safety for steel, which is 1.15, so 0.87, also the same as 1 over 1.15. Such that this is our design strength design strength of the design yield strength of the steel. Yes, we shall assume that the design assumes that the steel yields faster than it's meant to be. Then Z is the lever arm of the steel. You get this from the analysis of the section that ultimately meets the state. Okay. So whereby Z is determined by multiplying a factor LA by the effective depth of the section, whereby in our question the effective depth was given to us as 160 mm, but if you are doing a real project, you calculate for it by deducting the concrete covers and half the diameter of the rebar of the main steel. Okay, so and then this LOA also computed from, can be calculated from analysis of a section. It's given by that 0.5 root 0.25 minus 3k over 3.4, and this factor should not exceed 0.95. Okay, where k is our design moment over B breadth. Breadth of the section times the depth, effective depth squared, times the compressive strength, and it shouldn't exceed 0.167. Okay. Now we need to calculate for this parameter B, which be our effective breadth of our section. Sorry, I lost my drawing, but let's proceed. I escaped suddenly. Alright, so let's find out our B, breadth of the section. And the other point that you should note is that it is more economical to design a beam at mid-span as a T-section if it will be cast monolithically with a slab, like to be cast at once, which is always the case with these ribbed floors. The ribs and whatever and the slab are cast at once because they are a part of the slab. So, and in that case they end up appearing in this manner. whereby it is in this portion that we do fill our blocks, our hollow blocks. So instead of designing our rib as a rectangular section, in the real sense, part of this topping acts with the rib to boost the compressive strength of the section. That is for sections whereby the bottom part is in tension and the upper part is in compression. For example, the span regions, the midspan portion. So since concrete is good in compression, there is an effective width of this flange that will act together with the rib, such that it acts together with a portion of the rib above the neutral axis. So this portion here, this is the effective breadth. Effective flange breadth. So by designing the section in this manner, the section will be stronger than when it is designed as just a single rectangular section, whereby only this part provides the compressive strength. We shall not have utilized this advantage of the flange, so we shall have just neglected it, and by this we come up we end up with an economic design. Okay, so now let us now head on how determine our effective breadth. Okay, from Eurocode 2, this is the code that I use, or the code that we use in our country. It states that the effective the provided flange width, this is our rib spacing, it will be this distance B1 from the face of the rib to end of the flange on either side, plus the width of the rib. Likewise, the effective one will be the effective on this side plus the effective on the other side plus the width of the rib, the width of the rib. Whereby this distance, the effective distance of this is given by this formula. Either this or this is given by this formula. 0.2 of this very one plus 0.1 of LO, whereby LO for the end span, since we are designing for an end span, LO for an end span is 0.85 times the span itself. Okay, and this effective distance should be less than, it should not exceed 0.2 of that effective span, and also it should not exceed, it should not exceed this, which is already provided. Alright, so if we multiply 0.85 times our 5,000, our span, we get 4250 mm. And in this set means, like, since our ribs are our vertical spacing, which means this distance will be equal on either side of the rib, which is 400, which is our total distance, our total width of the flange, minus the width of our rib, which is 125, such that we, after subtracting this, we shall have remained with distance this side and distance this side, and since they are equal, we shall just divide by 2 to get the distance of 1, which is 137.5 mm. Okay, which we shall substitute into this equation to get the effective width of one side. For example, the provided B1, the effective B1 should be less than the provided. So now, to get the effective one of this is the formula, and since we have our LO, and that very distance, we can now get it, which is 0.2 times this 137.5 plus 0.1 times LO, which is 4050. We get this figure, but it shouldn't be more than 0.2 LO, which is this, which gives you 850, and it shows it shouldn't exceed the provided distance, which is 137.5. Okay, and the figure we get here is actually exceeds this limit, exceeds 137. It's less than 850, but exceeds 137.5. Therefore, we take this, which means the provided flange width is effectively used. It's effectively used, this B1, and by getting this, which means our effective flange width EF will be the width of the rib plus 2 times that, which takes us back to 400. So which means the provided width is the effective width of the flange. Alright, so at midspan the flange contributes to the compression area of the section, so we design as T section. As B is equal to B. So this is our widest breadth of the section, and we shall design for it. Okay. So now in our formula where there is B, we shall put 400, such that our K is 8.45 times 10 power 6 over 400 is our B breadth times effective depth square times 25, which is our compressive strength of the concrete, and we get 0.03, which is less than the limit. So okay. So we now go back and substitute the value of K in this equation. Okay, which is this, and we get 0.97, which is more than the limit, so we take the limit, which is 0.95. Alright, such that our lever arm's edge is 0.95 times the effective depth 160, and we get our lever arm as 0.152 mm. Sorry. Which we also substitute in our formula for area of steel required. This, and it gives us 128 mm. 128 mm. So from our steel tables, from our steel tables, 128 mm. So 128, okay, 12, 2 to 6, 10, 157. See. Okay, so we can provide this area 157, so which corresponds with two bars of 10 mm dia. Two H10 bars in the ribs. So we are going to provide two H10 bars in the ribs. Alright. Okay. Now for the first interior support, it is also at this point, or this section, it's where we get the greatest hogging moment from analysis. Therefore the steel we get from this section can be effectively applied to the rest of the supports, whereby still from our coefficients table, the coefficient remains the same, 0.08. Alright, and we get the same moment. So after getting the moment, we repeat we repeat the above procedure. And there is a point to note here that at the supports the flange is in tension, which is correct. At the support, the top bit of the section is in tension. So the portion of the section above the neutral axis is in tension. That's what it means. This is our neutral axis. This part will be in tension. And then this will be in compression at the supports. And therefore, since concrete is weak in tension, we design assuming that the section is correct and that concrete is not contributing anything, and that the steel is taking up all the moments. Therefore, the flange now does not play any part in resisting these tensile forces. Therefore, there is no need to consider it. So we design the section as a normal rectangular section. So, but the reinforcements we get, we distribute them across the width of the flange. And so after doing the design, still I got two bars of 10 mm there, so which should be distributed uniformly across the 400 mm width of the flange. Okay. Then the other issue is at the section where the ribs terminate. Which is 600. We provided that distance to be 600 mm from the center of the support. Since it's a support, the moment may be hogging. Such that the ribs down are in compression. Yes, if the moment is hogging, it means the ribs are in compression. So, which means they should provide that concrete area in compression to resist the moment. Okay, so now if we check their capacity, this is our moment of resistance of the concrete. This is formula from analysis of the section. Yes. And if we substitute in our concrete strength and the width of the rib, and then the effective depth, we get this capacity 13.36 kN/meter as our moment of resistance of the concrete or of the ribs. But remember, our sagging moment or our design moment in the span, mid span, was 8.45, which means, and since the span moment is 8.45, which is automatically greater than any other moment at the end support. This moment is automatically greater than the moment at the end support. So which means the capacity is automatically also greater than the bending moment at that support. Thereby making compression still not required at that section. Then for the top steel, and the end support, that one you provide steel basing on the curtailment rules. So now okay, allow me stop here. Then shall meet in the next tutorial as we talk about deflection, we talk about shear, and also we design for our topping reinforcement mesh. And by that we shall be through with the design of a ribbed slab. Please do me a favor, subscribe to my channel, view and also subscribe and also like the video. Thank you for your attention. See you.